Okay, let's get started. Get the lights adjusted. A very few brief announcements. First off, I graded your first set of meeting minutes, and to be honest, usually I have a couple groups that I kind of need to, provide some comments and say, okay, I don't think you all quite get it. You kind of need to beef it up a bit. Not really the case this time. I think y'all did pretty good. I was particularly pleased that every group is pretty much doing their own thing. They're not, taking, certain form and just copy paste. It's happening a little bit, but by and large, you all are taking the bull by the horns. At least it seems so from reviewing your minutes. I thought that was really good. The only thing I would mention, and I'm okay if this is in a like a cover sheet or a letter, but there were a couple teams that didn't quite include like a letter of transmittal. Some of you did that in a cover sheet, like you'd say, okay, here's meeting minutes number 1 submitted to Dr. Michelson on this date, and then some teams just said, okay, here's our minutes. Just some means of like a cover sheet or a letter transmitting the minutes. It doesn't have to be anything super fancy, but other than that, I thought you all did a very good job documenting your work. Really don't have any comments, so that's it. Y'all did great. Yes, yeah. There was no, but like there have been times where when it comes to the first set of minutes, I've had to say, okay, this team gets a 50, this team gets a 50, everybody else gets 100. No, everybody did great. Everybody did great. I did also upload this because I've been saying I was going to do that for a while, and I did. If you go under report submissions, you will see this. This is alternative reports guidelines. My plan is also to upload a rubric, like a grading rubric to go along with this. But, excuse me, this will give you just a general idea of what I'm looking for in your alternative report. Now, the first bit is things like a letter of transmittal, a title page, executive summary, table of contents. But really your alternatives report, when it comes to the body of the report, I'm thinking of 4 chapters. Now, when I say 4 chapters, it could be 5, it could be 6, and you'll see what I mean here in a second. But the first chapter should be the introduction to the project. And so chapter 1, in a nutshell, is sort of you regurgitating to me what's going on with this project. What are the applicable codes and standards? What are the potential design components? And we'll talk about that probably a little later. The scope of work, what your scope is, and then I'd like a general description of your alternative designs. And then there'll be after that, there'll be a chapter for each of your alternatives. So if you have 2 alternatives, there'll be a chapter 2 and a chapter 3. If you have 6 alternatives, there'll be a chapter for each of these alternatives. And you do whatever you think makes sense. If you think 3 alternatives make sense for your project, do 3. These chapter 2, 3, 4, what have you, they don't have to be 50 pages long. They can be pretty short. It doesn't really matter. I just want you to clearly describe each of your alternatives. So let's say for the sake of discussion you have 2 alternatives. So you'll have a chapter 2 on alternative 1, a chapter 3 on alternative 2, and then you'll have chapter 4, which is your selection methodology. So that could be cost, it could be construction time, it could be whatever you think makes sense. But I'd like to see a description of your selection methodology. I'd like you to take that methodology, compare the alternatives, select one, and then tell me what's remaining to complete the project. And that's chapter 4. So everybody okay with this? Okay, now as for appendices, let's see. Let me scroll down a bit. Now, you'll have Cad drawings, your project scheduling, Gantt charts and all that, all your weekly meeting correspondence. You'll have your alternatives report presentation, which, by the way, this is a question I commonly get. Let's say the report is due on the 15th, but the presentation is the 22nd. Can we change the slides in between that? Yeah, I don't have a problem with that. I just want you to have something in your report submission so that if Huntington, West Virginia gets hit with an EMP and we have no electricity for a week, that you have a presentation that you can go off of. That's a joke, but in all seriousness, I want you to have something in your report that can at least serve as the body of a presentation if necessary. And then finally, an appendix on notes, sketches, anything else that you think is appropriate goes in Appendix E. Okay, and so this is the alternatives report, and just so you're aware, the final report will basically be a Chapter 5, and then more appendices. So it's not like you're going to have to prepare a completely separate report. You're just going to build onto this. Okay, so I want you to kind of get an idea. As for formatting, I have some very basic formatting guidelines here. 12-point font, Times New Roman, 1.5 line spacing. Let's just keep it simple. Nothing fancy. Chapter headings, section headings, make sure you're using those properly. Include page numbers. Obviously, no spelling or grammar mistakes. We're engineers. We have a tendency to want to do that every now and then. Make sure that if you're using any standards, any specifications, software, guidelines, anything, that you're referencing it and spelling it out with a citation in the references. Now, as for references, is it APA, MLA? I don't care, as long as you're consistent. You know, use a formatting, use a reference system that contains all the fundamental information. Beyond that, I really don't care. I'm not gonna. At this point, we're sort of acting like grown-ups. So as long as you cite your stuff properly, I'm fine with whatever system you want to use. Figures, tables, and equations. Okay. Make sure that you're captioning those appropriately in the text. So, you know what I mean by that. You always put figure titles below the figure. You put table titles above the figure, or above the table. This second bullet where it says appropriate placement in the body of the report versus the appendix, one of the things about senior design is that you will have the tendency to produce a lot of tables and a lot of figures. Okay? So let's say we're talking about stresses or stress calculations or moment envelopes. You can get dozens and dozens and dozens of tables from that. But you don't need to include dozens and dozens and dozens of tables in the body of the report. That's what the appendices are for. Maybe include 1 or 2 in the body of the report to make the point that you're making when you're writing the report. But I don't want to be reading your report and then have to flip through 50 pages worth of tables. You know, don't do that. Use the appendix for what it's for. It's the appendix. It's there for a reason. So that's what I mean by appropriate placement. Figures and tables should be referenced in the front matter of the report. So there's a list of like there's a table of contents, and then there's a list of figures, a list of tables. Make sure that you're listing those appropriately. Any of the equations, you don't have to list those at the front of the report, but just number the equations sequentially throughout the report. You are going to have equations in your report. This is civil engineering. It is what it is. Don't list the equations in the front matter. Any standard specified equation should be accompanied by a citation. So m equals WL squared over 8, that doesn't come from a code or a specifying body. That's just statics. But something like the live load distribution factor for moments for interior beams, 1 lane loaded, that comes from AASHTO LRFT specs. So make sure that you're citing those accordingly. Last, your Cad drawings. If you've got Cad drawings, format those to be 11 by 17. Make sure you're including a title block. You all have had Engineering 102. You know the drill. You all have had Engineering 102. You know the drill. Make sure that you include a title block, north arrow, if appropriate. Depends on whether or not you're looking at plan, section, or elevation view. Include a scale also. And if you're looking at fabrication drawings, it is possible that there is no scale. And it's okay to put not to scale. That's fine. But put that. Okay? Also, what I don't want to see is, a drawing with text like this. Make sure the text is legible. Okay? Make sure that you can read the text if I were to print it out. Any questions? Don't worry, I'm going to try and provide a rubric for how I'm going to grade these soon. I'm actually thinking the rubric is going to be akin to what I did in civil engineering materials, if you remember the big concrete testing report at the end of the semester. I think I'm going to try and come up with a rubric very similar to that so you all have an idea of how I'm going to grade them. So, Sound good? All right. So here's what we're going to do today. Let me skip ahead a bit. So last time, if you recall, we were looking at section properties, and we were defining the various cross sections that we have to deal with when we're looking at staged loading, non-composite loads, composite loads, and the associated sections. And so what I'm going to do with you today is I'm going to help you write a pretty basic spreadsheet. Now let me be absolutely clear. In no way, shape, or form am I going to be, excuse me, in no way, shape, or form am I going to be formatting this to some standard. I mean, you're going to need to reformat this and make it look pretty and make it look professional. And I'm not going to worry about that with you all in here. But what I'm worried about more so is the math. So let's just go ahead and get right to it. What we're going to do is we're going to look at a given, just a generic bridge cross-section. Now this particular bridge has, it's a two-span bridge, and it has actually a girder transition near the pier. So if you look, you can see across the pier, the girder gets bigger. So what you're looking at is this is the top flange, this is the web, and this is the bottom flange as you go down. And here's the cross section of the bridge. So it's 4 beams spaced at 10 feet. The overhangs are 3'6". You can see that the slab is an 8.5-inch slab with a 1/2-inch integral wearing surface, and so on and so forth. So what we're going to do is we're going to use some of this data to compute some pretty basic section properties. All right, sound good? All right, so let me move this because I'm probably going to sit down for this. So there we go. Okay. All right. So I have here, we'll do a blank Excel sheet. And what I'm going to do is, let me zoom in a bit. We're going to enter in some pretty basic information here. So we'll say component, we'll say width, and we'll say thickness. Come on. All right. Okay. Now, right now, all we're looking at is the steel girder by itself. So I propose that there are 3 components we need to look at: a top flange, a web, and a bottom flange. Okay. Now, let me go to this this image right here. So what we're going to do is we're going to concern ourselves with this girder right here, this first section right here. This is what we would call sort of the positive bending region. This is the part of the bridge that's going to want a smiley face. So the top flange is what, 14 by 3/4? Web is 42 and 7/16, and then 16 and 1 1/4. So we'll say the width, we'll say 14. We'll say the thickness is 0.75. So this is 42. Now, as for the thickness, if you don't know what the fractional value is for 7/16, just calculate it. Okay, that's the beauty of Excel. Okay, don't try and enter it in. Just have Excel do the math for you. Okay, and this is 16, and this is 1.25. Is everybody okay with this? All right. Now, let me sort of format this up a bit. Okay. Okay, everybody with me so far? Okay. Now, you all can set this up however you'd like. What I'm going to do is set this up over here to the right. And if you've had me for steel design or concrete design or whatnot, you probably are going to, especially concrete design, you're going to recognize some of these calculations. So we're going to have a shape, and then I'm going to set up the following table. We're going to have A, Bless you. You all can sort of follow along with me again. Give me a second. Oh. I'll give you a sec. So we're going to set up a table very similar to this. So it's going to have AY, AY, and then I naught D and I. So if you, like I said, if you've had concrete design, you should remember this. And if you're in concrete design now, we actually just did this, what was it, Wednesday? I think we did a calculation just like this on Wednesday. Okay, everybody with me so far? Now, let's take this one step at a time. Okay, what is the area of the top flange? Like, how am I going to do that? Width times thickness. Now, here's the beauty of Excel. Don't enter in 14 times 0.75. Do this times that. Okay, because the idea is that if you change the value of the, let's say, the flange thickness or what have you, then everything else updates accordingly. And that's why Excel is so valuable in this setting. Okay? Now, if you set this up right, once you've done one, just copy and paste. Okay? As for the sum, there we go. Here, I'll just do that. Everybody with me so far? Okay, now, y distances. Everybody remember how the y distances work? We have to pick a common datum, right? And then we say the y distances are the measurement from that datum to the centroid of each individual shape. So what do you think is a good datum? Anybody remember? What do we usually use? The bottom, right? Okay, so let's take each of these one at a time. Let's start with the bottom flange. How far is it from the bottom of the entire section to the centroid of the bottom flange? Half the thickness. So equals that divided by 2. So one of the things I want you to start thinking about is I want you to try and think of this symbolically, because when we move into composite sections here in a sec, you really kind of got to think of this symbolically. All right, everybody with me with this? Okay, all right. Now what about the web? What am I going to do for the web? There you go. So equals that thickness of the bottom flange plus half of that. And then, so for the top flange, so we have the thickness of the bottom flange, the depth of the web, half the thickness of the top flange. So that plus that plus that divided by 2. What's that? Do I have a typo? Am I good? Okay, so next comes the AY column. And so all I got to do is equals that times that. And then copy and paste. Then I can copy and paste the sum. And there we go.
On the central calculations,
Yeah?
why are you adding the width to the thickness? Why is it not the thickness plus half the thickness?
Because it's always from the bottom.
But I'm just not conceptualizing this unless.
Okay. All right, hold on. Okay. Let's take the bottom flange. How far is it from the bottom to the centroid of the bottom flange? Okay. How far is it from the bottom to the centroid of the web? It's all of this half that. Now watch. How far is it from the bottom to the centroid of the top flange? All of this, half of that.
So why are you adding 16 instead of 1 1/4?
What? I didn't add. Did I?
The web is perpendicular to the flange.
Yes.
Oh, yeah, okay.
Yeah, remember the web is 42 inches tall, not
Yeah.
like 7/16 inches tall.
Okay.
That's why we stagger that. So I'm calling it the width of the web, but really it's the depth of the web. That's just sort of my way of making the spreadsheet tidy. So, all right. Everybody with me so far? It's just A times Y, just each one of those. And then just summing them up at the bottom. You want me to wait for a second, or are y'all good? Okay. All right, so let's take the moments of inertia. Okay, so remember, we have a rectangle, right? So what's the moment of inertia of a rectangle? It's BH cubed over 12. BH cubed over 12. The big thing is to make sure that you're using the right quantities. Remember, it's the width times the height cubed. Okay? So for the top flange, which is the width? Is it the 14 or the 0.75? The 14. So we're going to say equals 14 times that cubed divided by 12. So for the top flange, it's going to be tiny. That's okay. All right? What about for the bottom flange? Is it going to be 16 times 1 1/4 cubed or 1 1/4 times 16 cubed? It's going to be the same thing. So it's going to be this. But what about for the web? It's going to be backwards, right? It's going to be the 7/16 times the 42 cubed. So you'll know you've done this right. I'll show you something. So you're, give me a sec. You'll know you've done this right because what should happen is you should have really tiny values for the top flange and the bottom flange, but a really big value for the web. So that's completely normal. What do we think? So far, so good? All right, so now, what about these D distances? Y'all remember how to do that? Anybody remember that? What are those D distances? Oh, it's been a while, hasn't it? That's exactly right. It's the distance from each individual Y value to the centroid of the whole thing. Now, how do we calculate the centroid of the whole thing? What does that mean? Divided by sum of A, right? So what we can do is, so first off, like just over here off to the side, if I take sum of AY divided by sum of A, I get like 17.99 inches. That's the centroid. From the bottom, if I come up 17.99 inches, that's the centroid. Okay? So how do I compute each of these D distances? I take Y minus that, Y minus that, Y minus that. Now, does it matter which direction I do the subtraction? Like I could do Y minus that, or I could do this minus Y. Does the order really matter? Why? Why doesn't the order matter? What are we ultimately going to do with those D values? We're going to square them, so it doesn't really matter. But, okay, so what I'm going to do is I'm going to say equals this minus that divided by that. You can if you want. That's fine. The only thing to keep in mind is that you might have a tendency when you're building these tables to copy and paste the table over again. So just be careful with that. So here, I'm just going to type it out. So that minus that divided by that. So that's what I'm going to do. So depending on which way you did it, you should have 2 positive values and 1 negative value, or 2 negative, 1 positive. It doesn't really matter. But the values should be the same, the actual magnitudes. You should get something like 25.6, 4.25, and or 4.26, and 17.4, something like that. So far, so good? So does anybody remember what we put in this last column? I plus AD squared, exactly right. So we say equals that plus A times D squared. And then we can copy and paste that. Bam. And so if you did this right, you should get 15,969. All right, is everybody with me so far? You're shaking your head. What's up? Oh, it's a Mac. Let me see. So, you're going to take that quantity minus that. You're going to do that each time. Be careful. You can lock cells if you would like, or you can copy the formula over and over again. I kind of actually like to copy the formula over and over again because there's a chance that you'll copy and paste this table over. Okay, what do we think? Now here's the thing. During design calculations, y'all are going to be tailoring your flanges and webs, and you're going to be changing dimensions, quite a bit. You're going to be iterating this quite often. So what if one day you decide, well, that flange really needs to be 16 inches? Well, you change that to 16, bam, everything else changes accordingly, okay? And we're only talking about a very basic computation such as moments of inertia. These calculations are going to get intense real quick, okay? Because we're going to have DC1, DC2, DW calcs. We're going to have live load distribution factors. We're going to have a whole bunch of stuff going into this, and these calculations are going to get real intense real quick. And so being able to just click a button and everything else be updated, I mean, I really don't think let's just put it like this. You might appreciate it now, but you're really going to appreciate it later, okay? And that's just bridge engineering. There's really not much else I can get around when it comes to that. Okay. Everybody with me so far? Okay. All right. Now, let's take a look at something. So I propose that the non-composite moment of inertia of this section is something like 15,969 inches to the fourth. So first off, by now, I don't think I need to explain where moments of inertia come into play. I mean, if you compute deflections or you compute stresses, sigma equals my over I, deflections in a beam, you need to understand what the moment of inertia is. The problem is that is a non-composite moment of inertia. That's just looking at the steel shape by itself, okay? Well, what about if we're looking at the steel shape plus the concrete, okay? Well, what I want to do for the sake of this computation is I want to look at a typical interior girder, okay? So let me see if I can draw on this. Oh. Here, I'll do this. Let's just add a page here. Okay. So we're looking at a typical interior beam, okay? So what I need to know right off the bat for an interior beam is I need to know what the tributary width is. Anybody know what the tributary width is for this bridge going to be? 10 what? Feet. So in inches, 120 inches. So if we're talking about an interior girder, the width of that slab is going to be 120 inches. Now, let's see if you were paying attention from last time. What's the thickness of the slab going to be in these calculations? Well, hold on. So let me explain what that means before we answer. So it's an 8.5 inches slab with a 1/2 inch integral wearing surface. So what that means is that the total slab thickness is 8.5 inches. Okay, but a 1/2 inch of that is considered sacrificial. So if we're computing section properties, what's our slab thickness? 8 inches. Okay. Remember, section properties are a measure of the section's capacity, its strength, its resistance. So from a strength standpoint, we're only going to consider 8 inches. Okay? Exactly right. Exactly right. When we're computing loads, we take into account the 8.5. Okay? And so this is where the details come into play, and you really need to make sure that you're paying attention to what values you're using for what computations. Okay? Everybody okay with that? Now, we are using normal weight 4 KSI concrete. Okay, so normal weight concrete. Okay, so that's 4 KSI normal weight concrete. Okay, now in bridge engineering, that means that the E sub C is 1820 times the square root of FC prime, but in the land of bridge engineering, we put in KSI and we get out KSI. So I apologize for what we did last year in concrete design. We were putting in PSI, but the bridge spec is geared and written towards KIPS. So 1820 times the square root of 4. Square root of 4 is 2, so that's 3640. Did I do that right? So 3640, 3640 KSI. What is the modulus of elasticity of steel? 29,000 KSI. So what is N? So what does that come out to be? 7.97. Do I get a second on that? Okay. Typically, when we compute N values and when we use N values, we take the nearest whole number. So you'll probably compute an N value that's 7.97 or 8.96 or what have you. We usually round that to the nearest whole number and just take that to be 8. Okay? So, and if you're talking about a steel bridge, N equal to 8 is a very, very, very common assumption. So just right off the bat. That if I was, half asleep and somebody asked me what the modular ratio for a composite steel bridge would be, I would say 8. So I think I would. No, it has not. I don't know. I have no idea. That would be a story. that would be a story. All right. Everybody okay with this? So our modular ratio is 8. Okay, why does that matter? Okay, it matters because, let me go back to this image here. Remember, what we're going to do is we're going to try and compute section properties, but the problem is if we're looking at a composite section, that composite section is made of 2 materials. You can't compute section properties of 2 materials because flexural theory and basics of structural mechanics state that these, sigma equals my over I, these fundamental stress formulas, are all assumed that the beam is made of 1 material. So we have to transform it. We have to turn this lump of concrete into an effective lump of steel. And we're going to do that by converting it using the modular ratio. So this width for this interior girder is what, 120 inches? So what is 120 divided by 8? Just for discussion purposes, what is that, 15? Okay, all right. Y'all have calculators in front of you looking at me like, look, it's 15. So what we're going to do is we're going to convert that 120-inch wide slab of concrete into a 15-inch wide slab of steel, and we're going to compute the section properties of that composite section. Now, because we're dividing by n, that's a short-term composite section. If we were dividing by 3n, it would be a long-term composite section. And I'll show you how we can update that here in a second. Everybody with me so far? Okay. The only other thing that you need to be cognizant of is the haunch. Okay. But we'll get to that here in a second. Let's get some tables set up. So what I'm going to do is I'm going to sort of copy and paste this just to have all the formatting set up because I'm lazy. Okay. What we're going to do is we're going to do a new girder computation, a new cross-section computation, although we're only going to have 2 shapes. We're going to have the girder and we're going to have the slab. Okay? Now we're going to fill in these rows one at a time. We'll start off with the girder because this one's pretty easy. What is the area of the girder? It's right here. We don't need to recompute it. We've already computed it. Okay? So basically what we're doing is we're doing a cross-section computation, whereas before we were looking at a top flange, a web, and a bottom flange. Here, we've already got the top flange, web, and bottom flange figured out, so it's just the girder and the slab. Okay? What about Y? What do you think Y is going to be for the girder? How about that divided by that? Remember, what is Y? It's from the bottom all the way to the centroid. We already figured that out. That's 17.99. So what's A times Y? Bam. Bam. What? We already figured that out. It's just sum of AY over sum of A. How about this? What's I naught for the composite section, or for the girder? We did, and what is it? Exactly right. 15,969. Now we still got to do these and these. I'll worry about those later. Okay? Now, I'm not going to set up a table over here for the slab, but I highly recommend that you do that when you're setting up these spreadsheets. I mean, you can set up the spreadsheet, for instance, like if you input a girder spacing, it'll figure out what your effective flange width, and you could say, well, if I have 4 KSI concrete, what's the modular ratio? You all are smart enough with Excel, you can figure that out. I'm not going to do that here. But let's just sort of hard code this in, just A, because we're running out of time, and B, I want to make sure everybody's clear on what's going on. Let's first off talk about the slab. What is the area of that slab going to be? first off, what's the thickness? What do we agree on the thickness? 8 inches. And what is the width? No. It's 120 divided by 8, right? Remember, we're converting it into an effective lump of steel. So what we're going to do is we're going to take 120 divided by that modular ratio times the thickness. And so, yeah, I mean, I know you're looking at the numbers. Well, couldn't it just be 120? Yeah, the numbers will tell you it'll be 120, but I actually kind of want you to go through the practice of calculating that out, because instead of using the number 8, you could refer to a cell over here with the modular ratio. Okay, instead of using 8. What's that? Okay. It's this. Remember, we're turning that lump of concrete into an effective lump of steel. And how do we do that? We divide by n. And what is n in this case? It's 8, right? So we're taking 120 divided by 8. That gives us the width, and then we have the thickness.
Would you do something similar to that with the walls or the exterior girders?
Yes, exactly right. The only difference is this value would be different. It wouldn't be your girder spacing. It'd be half your girder spacing and your overhang. So that's a great point. You're going to have different section properties for the interior girder as you are for the exterior girder, because you're going to have a different width.
So, how do you know, do you always adjust the width and not the thickness?
Yes, that's a great question. The reason why is because your Y distance has to remain the same. Your moment arm has to remain the same. So how do you change the area but keep the same moment arm? The only way is to change the width. So that's a great question. That's a great point. Any other questions? This is good stuff. All right. Now, before we enter in these Y distances, I want to look at this. Okay? First off, let me press enter here. Now remember, this Y value, right? What is this Y value? It is the distance from the very, 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 very bottom, right, to the centroid of the deck. Okay? So I'm gonna draw this out, or I'm gonna type this out, and then I want to explain what I'm gonna do, or I'm gonna explain why I did it. Here's what I propose. I propose that to get from the bottom to the centroid of the deck, this is what we're going to do. We're going to take the thickness of the bottom flange, then we're going to add the web depth. Now, here's the thing. Instead of adding the top flange thickness, I'm going to add the haunch. Okay? The haunch in this instance is 2 inches. Okay? I'm going to add the 2-inch haunch, and then I'm going to add half the slab thickness. So I'm actually skipping that top flange, like I'm skipping it. Okay? There's a reason why. Exactly right. Exactly right. That's the reason why. All right? Does everybody have this? The slab thickness. No. The width is 15. Right. Everybody with me on this? The reason why is this image right here. Okay? Remember, the haunch goes from the top of the web to the bottom of the slab. So think, you go up that thickness, you go up the web depth. Would I add the thickness and then the haunch? No, the haunch already includes that thickness, right? So I go bottom flange thickness, web depth, haunch, and then half that thickness to get to right there. Does that make sense? Everybody okay with that? Well, if you've got that, then go here, bam, times bam. Excuse me. Starting to see how this is going? The only thing left is this moment of inertia. It's still a rectangle, so it's still BH cubed over 12. What is the B? How wide is that slab? 15. So the width is 120 over 8, right? Times, what's the thickness? What's the height? Say it again. 8 cubed, yes, 8 inches. So 8 cubed divided by 12. And if you've got that, then the rest of the table should be really easy to compute. We take our d distances, we say y minus that divided by that minus that divided by that, and then I plus AD squared. So right off the bat, the value is higher. Does that make sense? Well, it should. You're including a composite deck, so naturally the stiffness should go up. Okay? Now, if you want some names for these sections, let me put some names up here up top. So this first one, this would be the non-composite section. Okay? This second one down here, this is the composite section, but it is a very particular composite section. I propose that we would name this the short-term section for an interior girder. Why is it for an interior girder? Because we use that interior girder width. So how would this computation change, let's say, for an exterior girder? Well, it wouldn't be 120 inches. It would just be a different width. What would that width be? Well, it'd be whatever this width is from here to the end. And we would neglect that little fillet of concrete right there. So
What about your parapet?
that we would neglect that for structural calculations, but not for loads. Not for loads. Those are loads that are applied after the section becomes composite. So there's a name for those. We call them DC2. DC1 are loads that are applied before the section becomes composite.
So it's your, yeah, it's your
Exactly. One other thing, I'm calling this short term because I used an N value of 8. If I used 24, 3N, I would have a long-term composite section. And so the difference is long-term composite sections resist loads like the barriers. Short-term composite sections resist loads like the truck. So different sections for different loads. So right off the bat, there are 5 section properties or 5 sets of section properties you can compute right now. Non-composite, and then your 4 composite sections. 2 short terms, interior, exterior, and 2 long terms, interior, exterior. So you could actually set up 5 of these tables. And so I actually recommend that you do that. I also recommend that you make the sheets a little more dynamic. Here with the slab, I'm typing in the numbers. Like refer to numbers over here so that if your slab thickness changes or your girder spacing changes, that the tables can update accordingly. I highly recommend that you do that. We're going to be using these section properties sooner rather than later. So yeah. Sound good? Don't worry. We're just getting started. Monday, we'll probably get into loads. We'll actually start talking about DC1, DC2, DW, and live load distribution factors and all that fun stuff. That's all I got, everybody.